Good morning, everybody, and welcome to the today's security clinic. This session is going to cover an application security framework for digital financial services. So I'm Kevin Butler. I'm an associate professor of computer science at the University of Florida, and my research is on the security of computer systems. I do a lot of work in mobile system security, and I've been involved with looking at security in DFS for about 4 years now. With me on my right is Rehan Masood from the State Bank of Pakistan, who's going to also talk about an implementation of an application security framework used by the State Bank of Pakistan. I think you'll find this very interesting. So this session will be a little different from what you saw in the plenaries yesterday, where things were sort of by necessity, a little high level. I was planning to get a little more technical in this discussion, so just a quick show of hands. How many of you are application developers? Okay. How about MNO operators? Regulators? Okay, a couple. That's good. And then I suppose associated with finance. So hopefully, so how many of you have looked at code before? Computer code, C code. Okay. So we've got a couple. Great. Excellent. Again, this isn't going to be a coding exercise or anything along those lines, but the goal of this presentation is to dive a little bit deeper into how to develop that application security framework. We're looking specifically at smartphones, and we'll see some technical discussions about how best practices with regards to structuring those applications. So there's going to be a bit of a mixture of high level and lower level concepts. So but please feel free if you have any questions at any point. Just let me know. Feel free to just raise your hand and use the mic. I think the room is probably small enough that you'll be able to hear me even without the earpiece, but I suppose for the purposes of anybody who might be listening and on recording, please make sure to use your mic. And if you have questions, please identify yourself so that we all know who we're talking to. Okay, without further ado, let's talk about an application security framework for DFS. So you might be wondering, didn't I just hear about a framework yesterday during the plenary session? And that was the security assurance framework for DFS. So what is the difference? The assurance framework is really about looking at all of the different stakeholders in the digital financial services ecosystem. This talk is actually focusing on something that we spend totally about 2 pages talking about in the report, but in this presentation I'll go into much more detail. And this is really about applications, and it's about looking at what's going on the mobile device itself. And the focus of this template that we put together and of this discussion is on smartphones. So feature phones still clearly have a use. Their use is very widespread in a number of economies, but we've seen that the adoption of smartphones is happening very rapidly. And smartphones are a tremendous driver of innovation and adoption. Now, many of them, speaking as a computer scientist and as somebody who works in security, I've found that in the last 10 years or so, many of the most interesting things that have been happening from a security standpoint are happening. Traditionally, it's been servers that get security features first, and then personal computers, and then maybe mobile after that. But things have changed because of both the widespread adoption of smartphones and the tremendous amount of capabilities that these devices provide. So now we're finding that many of the most compelling security features are being found on mobile devices first. And so this really means that we've got a lot of opportunities to provide better security. Now, of course, the threat model is very different when we're talking about mobile devices as well. One of the big differences is, think of a server or think of a desktop computer, and then think of a mobile device. What's different? Well, a server might be sitting in a rack in your data center, or it might be sitting in your enterprise somewhere. Your desktop computers are fixed in place. Your mobile devices go everywhere you do, to an even greater degree than laptops. Your mobile device is always with you. They're effectively ubiquitous, and this means that if we're carrying a lot of private, confidential information, we're doing all sorts of computing on a device that's always with us, then the attack surface that we're facing is very different. The other thing that's really changed is that smartphones are always connected. So that means that you're always carrying something on you that is always connected to the internet all the time. This was almost unfathomable just a few years ago, that we effectively have direct connections to everyone and everything in the world all the time. So it means that we've got unique technologies for defense, but we also have unique types of attacks that are within the smartphone environment. And smartphones have only recently become a conduit for conducting financial activity, but the growth has been explosive. And then, like I said, mobile applications can potentially provide immense value from a security standpoint, but the threat surface is larger and the consequences are large as well. When you look at the number of mobile devices that are deployed, it's in the billions. So a major attack against a smartphone could have consequences of hundreds of millions or billions of users. Now, what is it that makes smartphones different from feature phones and traditional 2G networks? So, for one thing, one of the biggest differences is that we have an ability to change the security model in terms of what can connect, what is exposed from a data standpoint. So, looking at feature phones, for example, on your standard 2G GSM networks, there are vulnerabilities that are faced in a variety of areas throughout the MNO's network. So between the smartphone, or between the feature phone and the base station, you're going to have you may have some level of encryption, and this is going to depend on your jurisdiction. Some places are running a weak or non-existent encryption on the link between your phone and the base station, but you might be running GSM's A51 encryption or possibly A53. If you're running A51, that's known to be a weak cipher and it can be brute forced. What does it mean to brute force a cipher? It means that it's possible to totally enumerate all of the different ciphers that can be encrypted with that cipher. You can potentially generate the key. There are what are called rainbow tables that have been developed for A51, which mean that you can download these tables. The tables are about a little over a terabyte in size, and in combination with information that you grab over the air, you can use that in conjunction with your rainbow table to effectively decrypt the key and figure out what's being transmitted in any communication between the base station and the mobile device. So the encryption at the base station, between the base station and the device, is relatively weak. And then once information gets to the base station, it's effectively unprotected. It runs in clear text between there and the mobile money server. So what this means is that if you have any type of adversary inside the network, for example, a malicious insider, they'll have effectively full and unfettered access to any data that's run between the mobile device and the mobile money server, from the base station to the DFS services. And as I said, the link between the base station and the mobile device is also weak, and a determined adversary could potentially decrypt any information going across there and learn the details. So if you're running a financial transaction over USSD, for example, then that data can potentially be intercepted and read by an adversary. So from a security standpoint, again, it's important to know what your threat model is and who you consider your adversary to be and what level of risk you're willing to accept in the network. But these are things that are not really fixable with 2G networks and with feature phones. So what's the difference between this and smartphones? The key difference is that smartphones support so-called end-to-end security, meaning that because smartphones are generally more powerful devices, they have the ability to set up encryption on them that allows them to communicate directly with the DFS server. By doing so, you can effectively have a communication that is completely encrypted from the time it leaves the mobile device to the time it arrives at the DFS server, regardless of if anybody tries to intercept that traffic or tries to eavesdrop on that traffic anywhere in the network from between the mobile device and the mobile money server, it's not going to happen because there's going to be confidentiality guarantees that you have. You also have the benefits of integrity, meaning that you can tell if somebody's been trying to tamper with your messages. And this is because mobile devices use what's called TLS, or Transport Layer Security, which is the same thing that you use if you're ever banking with your bank, with your laptop, or with your smartphone. Whenever you see that lock, that green lock in your web browser, that's TLS at work. And so smartphones have the ability to make use of TLS to allow for this end-to-end security. And that's a big difference between what you get with feature phones and with smartphones. So if our adversary is anywhere in there, oops, actually, that's from the previous part. So no matter what happens inside the network, you should be pretty safe from tampering or from eavesdropping. Now, there are other things that smartphones provide that are uniquely different from other types of devices, and these are some of the new features that are being found. Some of them are already deployed in mass market devices. Some of them are coming, especially to lower spec devices. It seems as though a number of smartphone manufacturers are trying to ensure that some of these trust secure features are making their way, so that they're not just in high-end smartphones, but are increasingly going to be found in lower end and more affordable devices as well. Examples of these include secure boot, which effectively ensures the integrity of the device from the time it's booted. It's a way of effectively demonstrating that the code that's been loaded onto the device from the time you start it up until you're using it is all correct. And that's also related to what's called a measurement of the platform. Basically, whenever you start your phone, you have a boot sequence, you have an operating system that loads, you have various drivers that are also allow you to interface with the phone. All of those, you know ahead of time what those pieces of code are supposed to look like. So you can take what's called a measurement or a hash of each of those pieces of code, which provides you with a small value that you can be transmitted to your smartphone to your MNO, or held internally in the phone, and the phone can compare the calculations of the measurements that it's created compared to what it's expecting to see. And if those are incorrect, then it knows that something's gone wrong or somebody's trying to tamper with the device. This is a very important and means by which you can actually assure the load time integrity of your device. And then increasingly, we're seeing the use of so-called trusted execution environments. There's a technology by ARM, which is the predominant manufacturer of chips for smartphone devices. There's a technology called Trust Zone. And Trust Zone is a means by which you can effectively have two different types of computing happening on your same device. You have what's called the normal world and the secure world. And in the normal world, that's where your regular operations happen. And the secure world actually runs its own environment that is protected from the normal world. And so you can place sensitive information in the secure world and be fairly safe that information can't be exposed to the rest of your phone. So I'll talk a little bit more about that later in the presentation. We also have the ability to provide for what's called, where we have the ability to provide better authentication. You heard the talk on authentication yesterday with multi-factor, biometric, etc. We clearly have increases in what's available from an authentication standpoint on mobile devices. You've got fingerprint scanners. Increasingly, you've got iris or face recognition scanners. These are convenient and they're secure. So they provide us with a means of getting rid of passwords or supplementing passwords, and they can allow for far easier use of authentication. So, for example, I have one of the newer iPhone devices, and it's got Face ID on it. I didn't know what I was going to think of it because I thought, how secure is this thing really? It turns out that it works really well, and I actually run a password manager on my phone because I can't remember passwords. So and everything still uses passwords. So I'll store all of my passwords in a password vault, and then whenever I need to access my password, I'll just open my password manager on the phone. It asks me to do some sort of Face ID check. Let me pick up one password right there. So I'll load in one password. It asks me for my master password. I just press the button for Face ID. I look at it, and oh, look at that. It's authenticated. So the The face authentication is very. We haven't found, as a security community, we haven't found any real compelling breaks in Face ID. It's pretty secure. That's not to say that it's
Can I ask a question?
Sure.
We heard about the inbuilt in-screen fingerprint hack of news and Galaxy devices, and after which the banks stopped advise their users not to use banking apps on those Galaxy phones. Any update about that?
That's a great question. So yes, biometrics are not infallible, and neither is the code that runs them. So as far as I know, like I said, I think my Face ID is secure. If somebody is able to find a vulnerability in it, that's potentially a problem. But that being said, I think that's something that's this is one of the important things about sort of being vigilant about understanding what's happening on your devices. So as a regulator or as an MNO, having an ear to the ground in terms of what are the vulnerabilities that are being found in devices is important. I think for Samsung, it's both embarrassing and a big problem for them, I think. But knowing Samsung, they're going to have a patch ready relatively soon, I would assume. So that's generally what the case will be. If not, then it could be that entire class of devices might be considered unsafe. So, but in general, fingerprint scanners are actually they're good in the sense that they keep information on the phone. Your actual fingerprint or biometric is not transferred as per se to the provider. It's kept in that secure element on your phone, and only a representation or transformation of that data is sent. So that way, if your biometric is compromised on the server side, for example, then it shouldn't mean that your biometric, you can never use a biometric. It's not fully compromised for everybody. So mobile devices have these kinds of capabilities. So what we did with this template for application security was to define what are the general best practices for a mobile money smartphone application security framework. And we drew from a number of sources to do this. There was a study by the GSMA on mobile money best practices. I was actually involved in the authorship of that. The ENISA Smartphone Security Development Guidelines developed here in Europe. And actually, with Rehan's help, the State Bank of Pakistan's Mobile Payments Application Security Framework. They did an excellent job of putting some guidelines together in terms of how development should work. And we incorporated some of those into the template. So this template can be used as input to an application security policy by DFS providers. And regardless of whether you're specifically a provider, an MNO, an application developer, or even a regulator interested in sort of understanding what the security landscape looks like for these devices, our hope is that this template will provide you with some value. So the types of things that we considered include application integrity, device integrity, communication security, certificate handling, user authentication, secure data handling, and secure application development. So let me talk about all of those in some detail over the next little while. And like I said, if you have any questions, feel free to make this session as interactive as you like. I talk a lot, so I'm a lecturer in school, and I talk for 70 minutes at a time. So I could go all day, but yeah, if you don't want to hear my voice, please ask questions. So let's start by talking about device and application integrity. So what are the things that you should be concerned about from the standpoint of the device? Like I said, smartphones have a number of security mechanisms that are built into them, but the threat model is fairly unique. So actually, before I talk about anything else, I should define some terms. If you're not familiar with the term threat model, what is a threat model? This is one of the sort of the most important terms that we use in the security in security, because it's really a threat model is a combination of two things. It's a combination of the security model is a combination of two things. It's a combination of the threat model and a combination of the trust model. So the threat model is effectively an enumeration of all of the different ways in which an attacker can compromise your system. So what are the threats that your system faces? And the goal of the threat model is to define some parameters around it. Like you assume, for example, that the adversary is capable of doing certain things, and you design your system, because no system is 100% perfect. We can't defend against everything all the time. There's a number of things that you have to balance with security, things like performance, usability, etc. So the threat model helps you determine what is important to protect, and is your system protecting that. For example, we don't assume that our adversary has access to a quantum computer. If they did, we could potentially protect against that for certain types of defenses, but it might make things challenging from a lot of other standpoints. So the threat model is about what are the different threats that your system faces, and the trust model is trying to figure out what are the different components that your system relies upon. So when something is trusted, trusted sounds like a good thing, but in reality, if a component is trusted, it means that if that component fails, then your system is at risk. So, for example, the kernel of your operating system is trusted, meaning that if somebody broaches, if somebody's able to successfully attack the kernel of your operating system, then your system is going to be at risk. So what we hope for is that the things that are trusted are actually trustworthy, meaning that we have some sort of assurance that what we've trusted is actually in a good state. So so those are the two things that we think about when we consider the security model. So now, how does this relate to DFS applications and to devices? Well, the safest devices, one of the important things is assuring that the devices themselves are actually trustworthy before you engage in sensitive data transactions, such as sending money from a device. So the safest devices are those that haven't been jailbroken or otherwise rooted, because that means that if you've jailbroken a phone or if you've rooted a phone, then it may not be possible to assess the security of the phone. So what does it mean to jailbreak or root a device? You might have heard of these terms somewhere. So rooting a phone means effectively the ability to get administrator level access on a device, or root access. Root is a term that comes from Unix, meaning the most trusted user on the device. So if I've got root access, it means that I've got effectively what's often called super user access. I've got the ability to do effectively whatever I want on the device. I don't have access control constraints that apply to me anymore when I'm root. So now, similarly with jailbreaking a device, it's the same way of changing the way that the device boots, changing the underlying bootloader so that I have more control over the device. Now, that's fun if you're a hobbyist or a tinkerer, because it lets you do things with your phone that the company that made the phone wasn't necessarily expecting you to do. The downside is that it means that there's no way to assure that the phone is actually running in a state, because if you root your phone, it means that if somebody loads malicious code onto your phone, you might not be able to detect it, or if your bootloader is now malicious, you might not have realized that. So from the standpoint of a DFS provider, if you've got a rooted device on your network, you don't know whether that device should be considered safe for a user who's trying to conduct a transaction. That malicious code could be taking that transaction data and sending it off to somebody else, or it could be tampering with it as it goes along. So the safest devices are those that haven't been jailbroken or rooted. This process circumvents the platform integrity routines that I talked about, such as the secure boot process. So applications should use these mobile platform services to determine that they and the underlying platform that they're running on haven't been modified. Sure.
So can the app developers build into something into the apps to detect that some device is jailbroken or rooted, so that the DFS app cannot be installed on those specific devices?
Yeah, there are certain APIs that API is an application programming interface. There are APIs in Android that will allow you to assess the trustworthiness of the device and determine whether it's been rooted or not. So sometimes you might need to use some other measures outside, because if I've rooted a device, I can potentially lie about what I've done. But if I know, for example, what the set of integrity hashes should be on the device, then those are difficult if not infeasible, to fake. So if I ask for the integrity hash from the platform and I get it and it's wrong, then I know that there's a problem with the device. So there are ways that I can potentially check for that. And now some of the other things that are potentially important from the standpoint of device and application integrity, and this is on the application side, is that oftentimes when you're an application developer, you add additional code into your application. And you do this because it's once you've developed an application, it can be hard to test it after the fact. So often during development, you will put in some additional functionality. For example, unit testing of routines. That's good. That's good development practice. Or you may have an app where you have a sort of a common code base, and you might be deploying your application on a variety of different phones. So you might have all of the features turned on in your initial build, and you might want to be ensuring that all works on all of your devices. But when it comes to actually deploying your code for the particular mobile platform, and by platform I mean phone. Phones have different types of capabilities. Right? This is one of the things that marketers will do. They'll try to get you to buy one phone versus another because it's got additional features. For example, maybe one's got a fingerprint scanner and one doesn't, or one's got some additional security feature or some additional connectivity means like Bluetooth or NFC, and another one doesn't. So now, if I'm creating an app and I've got code for all of those things put into my application, and I'm deploying them on a device that doesn't actually have those capabilities, then it doesn't mean that my code is necessarily going to be idle. It means that the code is going to be there. But if there were any vulnerabilities in that code, then this is a vector that an attacker can potentially use to try to compromise the device. So any of this extraneous code should be removed from the application before it's actually deployed in the market or for that particular device. So remove that code that may have been added to the application during testing, or features that haven't been designed for the target platform before deploying the app in production. And then on the server side, as Rayhan mentioned, what can you do from the provider standpoint to actually assure that your application is running in hasn't been compromised? So you can assess both the integrity of the underlying mobile platform and of the application on the server side, and there are routines to do that. For example, like as I mentioned, taking a hash of the application and then sending that hash to the server is a good way of assuring that the code that you're running is the same code that you were expecting to run on the device in the first place. So, any questions so far? So, if you're not familiar with the notion of a hash function is it's a cryptographic primitive that effectively lets me take a piece of data of sort of arbitrary amount and compress it to a fixed length. So you might have heard of hashing algorithms. You might have heard of MD5, or you might have heard of SHA-1 or SHA-256. Those are so-called hashing algorithms. If I thought about it, I'd put some slides from my course on security that talk about it. But hopefully, if you've got the general gist of what they're all about. So I have an arbitrary length piece of code. I run it through one of these hashing algorithms, and it's going to create this fixed size so-called digest or hash of that piece of code or data that I'm hashing over. So with SHA-256, that's going to be a 256-bit code tag. With SHA-1, it's going to be 160 bits. Now, the important thing about these hash functions, a cryptographic hash, is something that if I have the hash function, if I have that little digest, that 160 bits or 256 bits, one of the properties of a hash function is that I can't take that 256 bits and figure out what it was that generated that hash. I can't go backwards from the hash and figure out how that hash was generated. This is an important property called pre-image resistance, and it's also it should be difficult, if not virtually impossible, for me to make another input that's going to hash to the same value as another input. This is called collision resistance. It's why if I have one value and another value, I should know that the hashes that they generate are going to be unique. If they weren't unique, then I could maliciously create another input that hashes. So, for example, if I'm doing an integrity check of the underlying platform, if I could make a hash function, or if I could make a hash value, a value that would hash to a legitimate hash, then I could make something that's malicious look as if it was actually non-malicious. So that's an important feature, and it's one of the reasons why some of the past hash algorithms like MD5 are no longer recommended for use, because collisions have been found in those hash functions, whereas functions like SHA-256 are still considered secure. So a hash function is an important mechanism. In fact, if you know about blockchains themselves rely extensively on hash functions to assure the integrity of the blockchain. So use hashing features to assure the integrity of the app, so that you know that what you've loaded on the device is actually what you're expecting. Okay, now from a communication security standpoint, we want to ensure that apps are using standardized encryption libraries. And so, like I talked about before, if you've gone to a website and you've seen the little lock in the in your browser bar, then that's some visual indication to you that you're using secure communication through TLS. TLS stands for Transport Layer Security. You might have heard of SSL before. SSL is effectively an older version of TLS that's been deprecated. TLS is an IETF standard, and it's been used just about everywhere. So current best practice is that you should be using, at a minimum, TLS 1.2. Why is TLS an important thing to use? It's because it's widely deployed. The protocol is openly available. There's no patent encumbrances on TLS. And every operating system library, both for mobile and desktop operating systems, have free libraries that are available for using TLS. So in general, a good general rule is, when it comes to encryption, use the stuff that's publicly available. Don't rule your own. Sometimes people have this idea that they can make their own encryption that's more efficient or that's more secure. They think they found a flaw, and they roll their own encryption. Encryption is really, really hard to do properly. It's why we find vulnerabilities even in things that have been extensively studied by experts on committees. So the chances of you, as a sort of an amateur cryptographer, developing a crypto library that is better than TLS is effectively zero. So if you or your application developer have decided to roll your own crypto, you should be looking at it very skeptically, and in general asking why am I not using something that's standardized. So TLS, like I said, is the minimum best practice that's used. TLS 1.2 is what's recommended. Because older libraries have issues. There's a wide variety of attacks against TLS that have occurred. Some of them have these catchy names to them, so that you can kind of remember them. This is an increasing trend in the academic research community, is to, every time you have an attack, create a nice, cute icon and a catchy name so that people remember what it is. For example, Spectre and Meltdown, you might have heard of, which are these microarchitectural attacks against processors. So there's attacks like Heartbleed, Drown, Poodle, Beast. There are many others. Robot. These are all, the specifics of them aren't terribly important for this discussion, but it suffice to say that these are ways in which the security of the TLS communication can be compromised. So, and some of these older libraries have issues because of these types of attacks. So, as a deployer of encryption services, you should be ensuring that you're using TLS. You should definitely be using TLS, and our recommendation is that everything should be upgraded to TLS 1.2 at least, in order to ensure the security of that communication. Now, increasingly, TLS 1.3 has just been approved a few months ago as a standard. It's got better performance, and it's got some better security features that are associated with it. It also removes a number of potentially insecure configurations that are possible in TLS 1.2. But it will likely take a few years till we see very wide adoption. So just know that it's on the radar, but it's likely not going to be It's likely not going to be in broad use in the immediate future, but it'll be increasingly deployed over the next few years. Now, within TLS, there are a lot of different algorithms that are used for authentication, encryption, and integrity. So authentication is about effectively proving the identity of whoever it is that you're communicating with. Encryption is about ensuring that nobody can eavesdrop on your communication. And integrity is about ensuring that your communication hasn't been tampered with. So you might be asking, what's the difference between encryption and integrity? Is it possible, if I've encrypted my data, then how can somebody tamper with it? Well, I could see your encrypted stream, and even if I can't read the information that's in that stream, I could potentially selectively delete parts of that stream if I've got access to it, or I could rewrite some of that data. If I know, for example, if I don't know what the contents are of an encrypted stream, but I know in general what the structure of the messages that are sent between two parties are, then, like I said, I could potentially drop some, or I could rewrite some and make one of them a garbage value. And if I do that, then I can potentially cause either improper encryption or the wrong logical flow to happen on your other side. So just because I've encrypted a communication doesn't mean that I can't tamper with it. That's where I need to have integrity as well. And integrity checks will ensure, they're a way of ensuring to the remote side that whatever information that is sent is the same information that has been received. So there are a lot of different ways for doing authentication, encryption, and integrity. And not all of them are considered secure for a modern deployment anymore, especially if the server is supporting something, a TLS version that's lower than version 1.2. And another thing that's important about TLS, or about encryption in general, is that the way that you encrypt information is also important. Now, why is that? It's because most encryption algorithms that we use for TLS are what are called block ciphers. So a block cipher is a type of encryption algorithm that takes your data. So say I've got a piece of data. I've got a file that I'm trying to send across a wire. Now, a block cipher is going to take that file and it's going to encrypt it in chunks or blocks. So an algorithm such as AES 128 is going to take 128 bits of a file at a time, and it's going to work on those 128 bits, and it's going to encrypt one 128-bit block, and then the next 128-bit block, and so on and so forth. And that's effectively many block ciphers are considered strong and standard. So things like AES, which is probably the best known and most widely deployed encryption cipher, is an example of a block cipher. So you take these data, you break it into chunks. Now, interestingly, the way that when you take data and you break it into chunks, the way that those blocks are linked together actually can have an effect on security. So I'll say ahead of time, though, this is one recommended mode of TLS operation is by using TLS with DHE RSA with AES 128 CBC SHA. You might be looking in that saying, I have no idea what any of those letters mean, but don't worry, we're going to talk about each of them in some amount of detail. So as I've talked about AES 128, AES stands for the Advanced Encryption Standard. It's a standardized way of doing encryption. But we don't need to get into the details of how AES works, although if you're interested, I'm happy to talk about it during the break. SHA is the secure hash algorithm. It's another standardized way of doing a hash function, and those are both considered secure. Now, CBC is the thing that matters with regards to our mode of operation. CBC stands for cipher block chaining. What this means is that when I have as I mentioned, in a block cipher, you have these blocks of data, and you take your data and you chunk it into these 128 or 256-bit blocks. With the CBC mode of operation, I will take that block of data and I will use it. I will feed that block of data into the next block of data, and then I combine that with the key to make the next block of data. And then I take that block and I combine it with the key to make the next block of data. Why does that matter? Because it turns out that if I take each of my blocks of data and I keep them independent of each other, I just encrypt one block with the key, then the next block with the key, you might think to yourself, well, all of my data is encrypted, right? So why would that be a problem? Well, let me give you a visual example of why that could be problematic. So the mode of operation where you take each of those bits of data and you encrypt them independently is called electronic codebook, or ECB. Now it's fast, it's parallelizable, and blocks are encrypted independently of each other. Now, why would this be that? Well, there's a great image that shows you what happens when you encrypt data with ECB. Here we go. So the image on screen shows the original image, which is our penguin here. Now, if I'm encrypting with any other mode of data other than ECB, for example, that CBC mode, where I've taken a piece of data, I've taken my block and I feed it into the next block with the key, then it'll effectively make what you would expect would happen when I encrypted a piece of data. It should effectively look like noise. There's no way for you to correlate this with the original penguin. But look what happens if I've encrypted something with ECB mode. You'll notice that it's something a little bit different compared to the other image here. So what do we see? We see, well, so the original was a penguin. We see something, it's not an exact. We don't have exactly the right colors, but you could probably look at this and say, that looks an awful lot like a penguin. So this is because of this notion of encrypting data independently of each other. So if I've encrypted this piece of data here, this is this area of black, and then I've encrypted this area of black. Well, because they're independent of each other, if I encrypt one thing that's black and I encrypt another thing that's black, or with those same values, they're going to turn out encrypting to the same value. So what this means from the standpoint of, if I have encrypted something that says, send $5, then that message, send $5, is going to look the same, no matter where in the transaction it happens. So I don't want to be able to independently figure out what a piece of data looks like, and that's why ECB mode is bad. That's why you should always be CBC, or why CBC mode is a good example of something that you should be using. And that's one of those parameters that's decided upon when you figure out how to do your TLS communication. Now, like I said, encryption gives you confidentiality, but it doesn't actually assure the integrity of your transaction. What you need often is to have a so-called message authentication code. So I talked about hashing, and how when you take a piece of data and you hash that data, you end up with a small value, so 160-bit or 256-bit tag or hash that's associated with the piece of data, and that can tell you that if you were to hash over that original piece of data, then you would also be able to reconstruct that same hash value. So if I was to send the hash value along with the piece of data, then you would know that you got the right one. Now, a message authentication code takes both the hash value and combines it with the key. And so if you know the key and you know what the piece of data that came in was, you can then also calculate that message authentication code, and you will know that the piece of data that you received is the same one that was transmitted. So that's an important thing from an integrity standpoint. So like I said, some hashing ciphers are good, like SHA-256. Some hashing ciphers are no good anymore. MD5 has been found to have collisions. SHA-1 is increasingly considered not secure. It's no longer recommended for use because researchers have started to find some breaks, some collisions in SHA-1. So there's no great issue with moving to SHA-256. So it's recommended that you do so. One of the things that's important is balancing performance versus security. For example, SHA-512 exists as a cipher, or I'd recommended AES-128. AES-256, AES-384, AES-512 also exist. These all mean larger keys, and you might say a larger key is more secure. Yes, that's true, but if there's also a performance impact. So the larger the key, the more computation you have to do. So there's no need to engage in overkill. You don't need to go to AES 512 right now, because currently, assuming that AES 128 is secure, which as far as we know is true, it'll still take the length of the universe to effectively decrypt a proper AES 128 conversation. You've got more than enough bits that you're never going to be able to brute force 2 to the 128. So we're probably okay. And so the recommendations that we have here take into account both a balance between security and what you should realistically be using in order to not be incurring a needless overhead in your system. So new modes of authentication include TLS 1.2 and 1.3, and these provide so-called authenticated encryption. But we haven't seen much client adoption of those yet. But you might expect to see those at some time in the future. So, right. So I talked about this notion of striking a balance between performance and security. So like I said, AES is fine for now, and AES 256 is probably not necessary. That doesn't mean that's always going to be the case, because cryptography is not, nothing is written in stone when it comes to cryptography, and when it comes to security in general. The technologies are always changing. Researchers are crafty and smart and are always probing these ciphers to look for vulnerabilities, and it's certainly possible that one will be found. A good example of this is the DES, the Data Encryption Standard. So in the 1970s, DES was introduced, and it was considered the most secure way of transmitting data. DES is a 56-bit cipher, meaning that there are 2 to the 56 number of ways in which you can encrypt something with DES. 2 to the 56 is a pretty big number for us to calculate in our heads. But for computers, back in 1976, 2 to the 56 was a big number. Now in 2019, 2 to the 56 is no longer a big number. So it's very straightforward to mount a so-called brute force attack against DES. Brute force means try every value and see if one of them works. And computers can do 2 to the 56. DES can now be successfully cracked by custom units developed for breaking DES in about 2 minutes. So it's no longer considered to be secure. So a variant of DES called triple DES or 3 DES was developed as a way of increasing the key length of DES and making it more secure. It effectively gives you 112 bits of security, which is pretty good. But other weaknesses have been found in DES over the last few years, and as of 2 years ago, the U.S. National Institute of Standards and Technology has deprecated the use of triple DES. So you should no longer be using it. Now, TLS will allow you to negotiate with DES, or with triple DES at least. Even TLS 1.2 will allow you to negotiate with triple DES, or maybe TLS 1.1. I'm not sure about 1.2. But any of these lower versions of TLS will allow you to create a negotiation with triple DES. So we actually asked ourselves, does this matter? Is TLS is triple DES still being used? And one of my students actually put together a study of over 36 million TLS servers around the world to determine whether DES and triple DES were still in use. And interestingly, we found that out of all of the TLS servers that we queried, over 40% of them supported some form of DES. Predominantly triple DES, because it's only been a couple of years since it's been no longer recommended for use. But it means that I can successfully create communication with a TLS server using triple DES, which is no longer recommended for use. So those types of connections should no longer consider to be secure, which means that if your server, if your TLS server that you're using for your mobile money applications is providing triple DES as a service, you should think about disabling it. So interestingly, we found in our study that, as we said, over 40% of the over 30 million, I think 36 million servers that we queried supported some version of DES. We even found both DES 56, which was that 56-bit version of DES, which is effectively, as I said, can be broken by dedicated units in about 2 minutes. And we even found examples of the extremely hobbled export version of DES 40, which is a 40-bit encryption that your smartphone could probably decrypt. And we even found examples of some of those being deployed around the world. So that's not good. If you're interested in this work, we wrote a paper. It was presented at a conference in Asia earlier this year. Now, we've talked about encryption and integrity. And first of all, before I go any further, does anybody have any questions about TLS or the use of authentication or encryption or integrity? Everybody with me so far? I know, like I said, this is a little technical in parts here, but hopefully, hopefully you're catching at least the high level details. So the way in which now what happens during TLS is that you've got a server that's going to communicate with you've got a server that's communicating with a client, and I want to figure out who it is that I'm communicating with. And so I'm going to start with the two of our two servers. Our client and server may not have an existing relationship with each other, so we can't assume, for example, that they share a key already. So what we're going to do first of all, before we do anything else, is negotiate which types of encryption algorithms we're capable of using. So the client is going to tell the server effectively, I've got this set of algorithms I'm capable of using. I can use AES 128. I can use AES 256. I could use triple DES. I can use this variety of hashing algorithms, and then the server is going to take those list of potential algorithms, and it's going to choose the one that it wants to negotiate with. So you should be setting up your server so that it negotiates with the most secure one possible. And if an insecure algorithm is presented, then the server should refuse the communication. Now, this is all done over so-called public key cryptography, meaning that the client is going to establish a communication using a public key algorithm like RSA. With public key, I can encrypt information that goes to the server, and only the server has the private key. So only the server will be able to decrypt that information. And so I will send some information to set up that communication. But once I've public key cryptography is not good for actually sending back and forth data after a communication's been established, because public key encryption is very, 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 very slow. So RSA, you might have heard of RSA before. RSA is the way by which it's probably the best known public key encryption algorithm. And it works based on some mathematics that have to do with how you factor integers. So when we talk about RSA 1024, we're talking about being able to factor integers that are 1024 bits in length. So think of a value of 2 to the 1024 is effectively the size of the numbers that we're looking to factor, which is effectively impossible for anything except for the most powerful computers to do. But there are ways in which you can verify that the factorization has been done properly. I'm not going to get into the details. What's important is that using shared key cryptography like AES is about 1,000 times faster than using RSA. So you use RSA to negotiate what key you want to actually use for communicating once the communication's been established. But important, that key is called a session key. So the way in which you actually negotiate those session keys can be insecure as well, because the ways what's often done is a type of negotiation called a Diffie-Hellman key exchange. Diffie and Hellman were two computer scientists who came up with this way of effectively being able to create a key over a channel without using encryption. It's a really neat mathematical construction. But the way in which you use Diffie-Hellman can be insecure. So the key takeaway here is that when in your TLS connection, you should be using a TLS DHE, because that's this so-called ephemeral Diffie-Hellman, which is more secure. Other types of negotiations are susceptible to so-called man-in-the-middle attacks, meaning that if I can misrepresent myself as the server and I'm not actually the server, I can pretend I'm the server. I can negotiate a session with you, and then I'm actually sitting in the middle between you. Here's the client, the server's me as the attacker. I'm in the middle, and then the adversary, the server that I'm wanting to communicate with, is somewhere over here. I can represent myself to the client as an adversary. I represent myself as the server, and over to the server, I represent myself as the client. And I can negotiate independently with both of those and actively interpose on communications. And so certain ways in which I negotiate keys, these types of man-in-the-middle attacks are possible. And you can imagine that that's a bad thing to have happen, because if I'm in the middle, then it means I can both see everything that's happening in a communication, and I can potentially tamper with information. So I want to make sure that I'm resistant to those types of attacks. So the way in which I negotiate keys is important as well. Now, every version of Android, and I'm focusing on Android here, though the advice is generally useful for iOS and other types of mobile operating systems as well, but Android is far and away the most deployed OS out there, so it provides a good standpoint for talking about these types of things. So all versions of Android have support for TLS 1.2 as long as they've been released anytime after 2012. So as someone who's deploying a service or who's regulating a service, you might look at you might ask your provider to do a check on what types of the versions of TLS are being deployed by your clients. So you can assume anything that's been released in the past 7 years supports TLS 1.2. Now, are there a lot of devices that are on your network that are more than 7 years old? The odds are probably fairly slim, but it's perhaps not impossible. But in order to assure the security of the users and their devices, you might want to mandate that you're using this version of TLS 1.2, but that means then that everybody who's using it has to have a phone that's been released in the last 5 to 7 years. So that's something that you might need to make a decision on based on usage that you found. But at least a good first step would be asking your provider to give you some information about the types of connections that are made, so that you can assure that high security connections are being made to protect the users. Now on the server, there's a number of pieces of best practices that we provide as well. For example, so during that TLS connection, what I'm going to get when I start the communication is the server is going to provide some information about who it is. So this is as a client, I'm connecting to a remote service. I don't know if I've connected to the right device or not. I don't know whether this is some service that I should trust. It's up to the server to assure me that I'm talking to the right server. So how does the server actually do that? Well, it's going to provide a so-called certificate. So what is a certificate? It's a piece of code that gives me some assurance about the trustworthiness of the server that I'm connecting to. It says that I am who I say I am. So, for example, when you go to your bank, you're going to get when you open your TLS connection, you'll get the certificate that says, I am whichever bank, Bank of America, Citibank, HSBC, and it'll give me some information about who signed the certificate, what type of encryption is being used on that certificate, what the lifetime of that certificate is, and it may in turn be signed by somebody else. So how do I know that this is actually Bank of America? Why should I trust this certificate? It's because that certificate is in turn signed by somebody else. It's signed by a so-called certificate authority. And certificate authority is something that you inherently trust. It's sort of the top of the chain. And often in your web browser, for example, you're going to have a number of these root certificate authorities baked into your browser. So these will be folks like Symantec or Komodo or what have you. There are a number of these that are baked in by default into mobile phones and into laptops and desktops. So, question? No. Mm-hmm.
So how would the server know the client, the certificates the client is presenting for the handshake? Are those there which are eligible to establish a connection?
Oh, that's an excellent question. So typically with TLS, typically we don't do so. Usually we care about server authentication, and that's sort of because of how the internet has evolved. The growth of the internet is more or less directly attributable to mobile commerce. So the servers themselves, things like folks like Amazon and Google, they care that you can authenticate who they are because you don't want to be sending your money to the wrong client. They've been less concerned in the past about who the client actually is that's being communicated because they want to make things as frictionless as possible. So generally, we see server authentication, but we don't see client authentication. so much. Now, if you want to have bidirectional authentication, that's certainly possible with TLS, which then means that when you start a TLS session, then the server will transmit a certificate, and the client will also have the certificate that's been developed by a CA, and the CA will present, or the certificate will present the client will present that certificate to the server, and the server will also go through a similar procedure of validating the certificate, which should also be signed by a CA in order to establish the authenticity of that client. And that's something that you might consider doing as part of your DFS system, is enforcing client authentication as well, where clients also carry certificates. So now the way that this works is because both sides trust that there's a certificate authority, and that certificate authority's job is to effectively act as a trust anchor. It ensures that the communication. It says, I vouch for this website. I vouch for this certificate, and you trust me because I'm known to be trustworthy. So all of that works as long as the CA is trustworthy. If the CA is no longer trustworthy, then that's a problem. So so you might want to have a contingency plan in place if your certificate authority fails or is no longer trustworthy. And this does happen sometimes. A few years ago, there was a certificate authority that was being used in the Netherlands, and this CA, I forget the name of it now, but the CA ended up issuing. They were either hacked or they inadvertently or otherwise issued some bad certificates that gave you root CA trusted certificates to a variety of organizations that shouldn't have done so. So if a root CA signs a certificate as if it was itself, it gives anybody who holds that certificate the same power as the root CA, which then means that I could be a malicious site and I could say, I'm now Google.com, but here's my certificate, and because it's signed by a root CA, you'd say, oh well, I trust this certificate because it's been signed by this trustworthy CA. Meanwhile, I'm not actually Google.com, but I'm more than happy to take your information and steal your money. So when this was discovered, there was a process of revoking the certificates, every certificate that the CA had issued. Now, what happened in the Netherlands is because this was a Dutch company, there was a lot of interest in sort of supporting them as a CA. So the Dutch government ended up having all of the majority of the certificates that were issued on Dutch government computers were issued by the CA, which meant that when the certificate was revoked, that now it was no longer possible to create an assured trustworthy connection to any computer inside the Dutch government, because whenever you would go to a server, you'd get a message in your browser saying this connection is not secure because I don't trust this certificate anymore. So this is a big problem. So it's worth having a contingency plan in place for what happens if your CA fails. Now, another thing that's important is to ensure that your certificates don't last forever. It's possible to create a certificate that will last for 10 years or for 20 years. But as we've talked about, what's considered best from an encryption standpoint changes. So I don't want my certificates to be valid if they're telling you to negotiate using outdated modes of encryption. And if, for example, something happens to the certificate, I don't want it to live forever and still be potentially good. So I should really limit the lifetime of the issued certificate. So best practice is that they should be limited to 825 days. I should also not offer certificates that have expired for my clients to verify. It's not that expensive to get a new certificate, and so don't try to save a couple $100 to get your your certificate renewed. Because if I'm a client, if I normalize my clients to just sort of clicking OK, yeah, this certificate is expired, but what does it matter? It's probably fine. If I normalize them into bad security practice, then when somebody malicious actually offers up the wrong certificate, you've already normalized them to just click on the button and say, okay, ignore the security stuff, and now they're at risk. So don't offer expired certificates for clients to verify, and make sure as a provider, as a regulator, etc., that all of the certificates being offered by your providers are non-expired and are not self-signed either. Now, you probably don't need to go the extended validation route for extra money. you can get so-called extended validation certificates that are supposed to be even more secure than standard certificates, but I've never seen the business case for why this would be worthwhile. So if you're looking to save money, don't save it by offering expired certificates. Save it by not mandating the use of extended validation certificates. On the client side, smartphones will they have the means to properly check to see that connections are being made properly, including a valid certificate. But what we've seen in practice is that a lot of applications will override these checks, often because during the development process, you're doing some testing as an application developer. You get all these annoying certificate checks. Perhaps you're not actually connecting to the final machine that you're going to be using, so the certificate's going to be wrong, so you throw an error. And so what will happen is that often these application developers are going to comment out the bits of code that do the certificate checking. Now, sometimes what happens is that those comments that have been commented out stay commented out in the actual production version of the code, meaning that now your application is no longer doing any type of validation because the developers commented out that checking code, or have overridden it for some way. So bypassing server validation and server authentication should never be done in production code. It's really important for that to be there, because without that, you don't know as a client who you're connecting to. And that's a great opportunity for somebody malicious to hijack your communication and hijack your financial transactions. Trusted certificates authorities should be stored securely in the client. And in Android, as an example, there are ways for doing this. There's a facility called the Key Store in Android that allows you to store information with strong cryptography on your computer or on your device, or for devices that have trusted execution environments, will allow you to store that private information in the secure world so that it's not accessible by the rest of your phone. There's also a technique called certificate pinning, meaning that once you've seen a certificate, you expect to see that same certificate over and over again. And if something changes, then you get alerted that you're seeing a different certificate. So this is a way of ensuring that nobody's going to change the certificate and ensuring that you're not taking a false certificate by accident. And there are APIs inside of Android that allow you to do this certificate pinning as well. These are all things that are done on the client side, and these are best practices that your mobile money application should be doing.
Small question.
Mm-hmm.
So, requiring these certificate pinning and all this certificate validation from the client side, does it hamper customer experience, user experience, or does it cost more to the DFS provider to require all these checks?
A great question. There shouldn't be any reason why there's anything. There's no additional costs that are involved to actually having these deployed on a system. With certificate pinning, the one issue is if you change your certificates often, then you might see errors, because if you're expecting to see one certificate and the server has changed its certificate, which can be good practice to do it periodically, then you might see an error that's thrown. So you may need to do some additional checking inside the application to ensure that if there is an error thrown during certificate pinning, that you go and just revalidate what the server actually is. But from an actual day-to-day cost standpoint, the costs are effectively zero for doing this.
And user experience?
From a user experience standpoint, this should all be completely transparent to the user. So again, it might be making your application developer do a couple of things, but this is literally 10 lines of code, so it's not a major burden on them either. From an authentication standpoint, pins and passwords should not be easily guessable, and weak credentials shouldn't be allowed. That being said, you shouldn't force the user to constantly change their password. Best practices for the users to not. You might work somewhere where the corporate policy is change your password every 30 days. Ensure that you haven't used the same password that you've used in the last 6 months. What usually happens, it usually means that, say my password was password 123. Okay, I've got to go change my password. Well, I don't really want to, I already know what my password is, and I can't be bothered to make any big changes. So the next time I change my password, it's going to be password 1234. And then 30 days from now, when they make me change my password, it's going to be password 12345. And so, the more that you make your clients have to go and come up with passwords that they change, the more likely are they to just write it down and put it on a sticky note on their thing, or to come up with something that's easy for them to remember, and which also makes it easier for an adversary to remember. So what's considered best practice is have one good password and just keep using that password, because a strong password is probably not going to be easily guessed. So something that's truth to tell, I have one password. I probably shouldn't be saying it publicly, but I've been using it for the most part for about 20 years now. It's like 16 characters long. You're not going to be able to brute force it. It works pretty well for me, and it's good. I mean, I have a couple of different passwords I rotate through, but the whole point is that if you have one good password, just use one good password. There's no need to have to be forcing someone to change your passwords all the time, because the threat model is not going to be that somebody's going to brute force a well-designed password. It's going to be that they're able to guess a password that you force them to change. And as we talked about before, multi-factor authentication is strongly encouraged, especially before performing financial or other sensitive transactions. And that's an easy thing to program. Before you allow a transaction to happen, have something that pops up on screen that says authenticate you are who you say you are. That way you know that somebody hasn't stolen the phone from whoever it is that's using it. And things like biometrics can make this effectively frictionless. Now, perhaps a little controversial, but hopefully makes sense, especially in light of the presentation about SS7 yesterday. Avoid the use of SMS as an authenticator. Why is that? Because SMS one-time passwords generated by SMS can be intercepted by SS7 hijacking, as Asaf was attempting to show in his the PayPal demonstration yesterday. So SS7 is not a secure means of doing things. And on smartphones, we have ways that we can avoid the use of SMS altogether. You can use smartphone authenticators, where information is transmitted by another channel that's still over IP instead of using the insecure SMS network. So things like Authy will allow this to happen. And there are well-designed APIs in Android for doing biometrics like fingerprint authentication. So your application provider should be making use of those. Modern devices have many mechanisms to support trustworthy data handling. I mentioned the Android key store before, that can keep data either encrypted or within a trusted execution environment of the secure world on your device. This type of there's specific APIs that are used for Android 6.0 and higher that'll effectively allow you to easily check whether information came from a secure environment or not. And you can actually provide an interface to retrieve these attestations from the secure hardware itself. So all of that is available to you. Some of these are only doable on more modern devices, but again, your application developer can easily have bits of logic in their code that say, what version of the device am I deploying on? If I'm deploying on a more modern device or that supports a more modern version of Android, then I can make these services available. If not, then I will sort of roll back to these other types of services. So, things are getting better. But even going back a couple of years and using those types of mechanisms, you still have a lot of opportunity to do things that are secure. Question?
Sorry, on the previous slide, I wanted to ask about, okay, so for instance, in my country, we use a mobile money transfer service known as M-Pesa, and the user authentication mode is actually a 4-digit password. So I'm wondering, in that case, then, I don't know, what's your comment on that?
Well, 4-digit passwords, again, the attack surface for 4-digit passwords. If I have a 4-digit password, then I have 10,000 options for what that 4-digit password can be. So depending on how I'm doing authentication, that can be sufficient, or it might be problematic. If all of my data is if all of my authentication is online, and I say I only have 3 guesses and then my account is locked, then a 4-digit password is I'm only going to be able to guess 3 times as an attacker before I lock your phone or I have to call in to customer service. If this information is being kept somewhere on the remote side, and an adversary gets access to that remote password database, then brute forcing 10,000 values is pretty straightforward. So I would probably prefer to see longer pins than 4 digits, because four digits is a relatively small space. But I think it's going to be really dependent on your use case. So Yeah. Okay. Yeah. Right. Yes, we're breaking in. Right about now. So let me just say a couple more things about secure data. Use TEEs when they're available. Delete confidential information from memory when it's not being used. Use fine-grained information. Don't allow external access to external storage, because when something goes out externally, it means that any other application can access that data that's on the external that's externally provided. So always validate your input that's coming in from the client, because they can be potentially trying to mess with your code. So I promised a comic yesterday. We have the infamous Bobby Tables here. It's a idea being that if I allow anything that comes in from a client, then the client can write whatever they want, and if I don't validate what they're writing, then I can cause serious harm to my actual system. So validate your input, especially if data is going to be stored in a database. And then finally, develop applications according to industry accepted secure coding practices and standards. Assure that there's means of updating applications, and assure that those libraries are secure. Provide updates when required, and have code independently assessed and tested by internal or external code review teams. It's important that whoever's testing is different from whoever it is that's developing. The developers often get very attached to their code, and they don't like hearing that there are problems with it. So it's important to have an objective third party. This can be inside, and the testers. Again, nobody ever likes the testers, but they do a very important job of ensuring that your code is secure. It's a whole lot better for issues to be found inside than having your code be deployed outside and having to go and then deal with a PR problem of an insecure application after the fact. So good practices revolve around basic security principles. The template that we provided gives a starting point for ensuring authentication, access control, integrity, and confidentiality. We didn't specifically talk about privacy, but that's an important factor to consider. And much like we talked about with the framework yesterday, this template is also the case for, and perhaps even more so because we're being a little more specific in our recommendations. The technologies change, so specific recommendations might also change. But the technologies change, the attacks change, the vulnerabilities change. But the long-term trends are fairly clear, and the fundamental basic security principles are a terrific starting point. So just be vigilant and be aware of what's happening. Make sure that your providers are also aware of what's happening from a security standpoint. And sort of everybody working collaboratively together can assure that applications are secure, and so are the users that are using your mobile money system. So we're at a break right now. I'm happy to take any questions during the break, or if you have questions at the beginning of that session, I'm happy to take them then. So we'll take a break right now, and thanks for your time.